Hey guys, today I would like to talk about mole ratios and mole to mole conversions as we continue our exploration into stoichiometry, which is cooking with chemistry. Uh, Today we're going to cook some hot dogs, but in order to cook some hot dogs, we have to cook some propane. Propane is this stuff right here, C3H8, methane, ethane, propane. It's a hydrocarbon, contains nothing but hydrogens and oxygens. 3 carbons, 8 hydrogens. We're going to react this with O2, atmospheric oxygen. These are all gases, by the way, and we're going to create CO2 and H2O. Um, you have a tank of propane under your gas grill. It's a liquid in the tank because it's a liquid under pressure. And you have a finite amount of propane in that tank. You're going to burn up that whole entire tank, and all the propane will react, but you'll still have plenty of oxygen left over in the Earth's atmosphere. As long as there are still trees, we'll have an excess of oxygen. So this is an introduction to the concept of what's called a limiting reactant, but I'll get into that later. So here's our recipe for burning propane. But you'll notice we're disobeying that law of conservation of matter thing, so I'm going to balance this out. I've got 3 carbons here. I've only got 1 there, so I'll put a 3 there. And then I'll do my hydrogens. I've got 8 hydrogens here and 2 there, so I'll put a 4. And if I look at my oxygens, I only have 2 here, and I have a total of 6 here, 3 times 2, and another 4 over here. And that gets me up to 6 and 4 is 10, so I got to put a 5 there. Now, this is my recipe. 1 molecule of propane reacts with 5 molecules of oxygen to create 3 molecules of carbon dioxide and 4 molecules of water. At the atomic scale, the microscopic level. To scale this up, to do this at a macroscopic scale, I've talked before about Avogadro's number. We're going to do this reaction Avogadro's number worth of times, 6.02 times 10 to the 23rd times. And I can write this now, I can understand this now, that 1 mole of propane plus 5 moles of oxygen reacts to form 3 moles of carbon dioxide and 4 moles of water. Now these are big macroscopic amounts, and that's my recipe. Now, what is a mole ratio? Well, what's a ratio? A ratio is, I don't even know how to say it, a ratio between 2 things. So if I could look at what's the ratio between propane and oxygen? It's 1 to 5. So for every 1 mole of propane, I can write this out. Let me switch colors here, Control Z. I can say that for every 1 mole of propane, you require 5 moles of O2. That's what my recipe says. Okay. I can also say, you know what, for 5 moles of O2, I need, for 5 moles of O2, well, I need 1 mole of propane, but for 5 moles of O2, I can produce 4 moles of H2O. So if I put 5 in, I get 4 out. So these things here, these are the mole ratios. Mole ratios. All right, so you just look at these 2 things and go, what's the relationship between any 2 of these things? Well, to make 3 of these, I need 5 of those. If I make 3 of these, I'll make 4 of those too, et cetera, et cetera, et cetera. So that's the concept of a mole ratio. Well, okay, now that I know that, well, how do I use these mole ratios to use my recipe? Because we're going to cook now. Well, let's take a think about some of these things. Let's say this. How many, oops, let me write with a pen. How many moles of CO2 will be produced? Let's see, how many moles of CO2 will be produced from an amount, let's say 4 moles of CH3, C3H8 of C3H8. This is propane. So what's this question asking? How many moles of CO2 would be produced from 4 moles of propane? Well, if I put in 1 mole of propane, I get out 3 moles of carbon dioxide. That's my mole ratio. If I put in 1, I get out 3. I'm not putting in 1, I'm putting in 4. So what I'll do is I'll use my mole ratio and I'll say right on. Well, for every 1 mole of C3H8, for every 1 mole, I'm going to make 3 moles of CO2. Okay. And it turns out that I will make 12 moles of CO2. And that's how you use these mole ratios. So let's say I had 4 tanks of propane, which is not 4 moles of propane. I could do 4 tanks, I could do 4 moles, just do it 4 moles. If I put in 4 moles of propane, I'm going to get 12 moles of CO2 out. That assumes I have way more oxygen than I need for this 4 moles. Right? Those 4 moles are going to require a certain amount of oxygen. I could calculate that too. It's going to be 20. Having said that, let's see, next problem goes a little something like this. How many moles of H2O could I produce from, all right, I'm going to try and make some water now. I'm going to try and make some water. How many moles of water could I produce from 8 moles of O2? So let's say I started with 8 moles of O2, how much water could I make? Well, if I start with 5 moles of O2, I'll make 4 moles of water. So my mole ratio is 5 to 4. I'll set up my problem here, and I will say that, well, for every 5 moles in, 5 moles of O2, I'm going to make 4 moles of water. I don't need to switch colors on you guys. I hope that's okay. A little bit more efficient. 6.4. 8 times 4 divided by 5, 4/5 of 8. 6.4 moles of H2O. Bada boom. That's how much water I could make. All right. I got another one for you. Last one. How many moles of propane? How many moles of propane required to make? How many poles? So we're going to make something now. Okay, I got some propane. I'm going to make one of these things. How many? I'm going to try and make some CO2. I'm going to make 14 moles of CO2. So for some reason, you're making carbon dioxide. If you work at a dry ice factory. Not the most efficient way to make dry ice. Considering that the CO2 in this case is a hot gas. You have to cool off into a solid. Probably take atmospheric CO2 and cool it off. But anyways, 14 moles of CO2. That's what I'm going to try and produce. How much propane do I need? Well, 1 mole of propane will make me 3 moles of CO2, assuming I have enough oxygen. So I can set up another mole ratio, and I can say that for every 3 moles of CO2 that I want to make, for every 3 moles of CO2 that I want to make, I require 1 mole of C3H8, 1 mole of my propane, and it works out to exactly 4.7 moles of C3H8. And that's how much propane I would need. There you go, cooking with chemistry. So that's how we use balanced chemical equations and mole ratios to figure out moles of different substances that are required or produced when we do chemical reactions. I found a new button over here too, which is kind of funny considering we're talking about the combustion of propane. This is the bomb button. There you have it. Don't forget to slap the like button and subscribe to my channel.